This is the first time I'm kind of doing a keynote. And when I started this talk, I honestly didn't really know what I wanted to talk about. There was a serious amount of doubt on my end. So I figured, how do you do a keynote? Well, maybe start with a blank canvas. That felt like kind of the right thing to do. And then eventually that led me to come up with a talk title. And that's when the ball really got rolling. So this is what I'm going to be talking about today. And I'm honestly very excited about it too, because basically what we'll be doing is we're going to talk about ideas that are worth thinking about. And I think it might be fun to start with what I think has been the most thought-provoking article of the last year, at least to me. So what I'm going to do now, I'm going to start by talking about a data set. And, this is a data set with stuff that comes out of a smartwatch. So you got to imagine we've got about 1,800 people. We've got their body mass index. We know whether or not they were male or female. That's also in this data set. And we also know the steps per day. So this is definitely one of those smartwatchy data sets. People track themselves, that sort of thing. But this is not the most interesting part about the data set just yet. You see, this data set was used in a statistics course. So a university with master's students, master's degree in statistics, if I recall correctly. So these are people who are used to looking at data. And they kind of figured, well, we're interested in understanding how people analyze data, so we're going to give this one group a couple of hypotheses to check. So you're given a data set, and you're given some hypotheses. So things like, check the correlation of the number of steps and the body mass index for men, compare that to women, check the difference in number of steps, men and women. These are hypotheses to check, and then by doing that, you'll hopefully understand the story of the data set. And then the other group, they just said, well, just look at the data. Just have a look. What conclusions are there in this data set? And here's what the data set actually looks like. So on the x-axis, you can see the number of steps. On the y-axis, you can see the body mass index. And whether or not it's a blue or a red dot means if you're male or female. This is obviously a synthetic data set. But the question is, which of these two groups actually found out? So we had the first group who got a couple of hypotheses to check, and the other group didn't get hypotheses to check. They are both from the same class, right? They're kind of randomly split. But it turns out that the group who didn't get a hypothesis was way more likely to understand that the data set was just nonsense and that there was a gorilla in the data set. And to me, that felt extremely thought-provoking, because if a hypothesis can be a liability in the field of statistics, what can be a liability in our field? Because you would, I had a couple of classes in statistics. You're supposed to do hypotheses. But apparently something about that makes it hard to find this gorilla. So that, to me, is extremely thought-provoking. But it also reminded me of something that happened somewhat early in my career. So I was at this website, company behind the website, obviously. And this website was trying to recommend secondhand cars to people. That was a use case that they had. And if you want to recommend things, you think recommender algos, let's go. So you read the book, and you quickly learn about these algorithms like matrix factorization. It was a little bit before neural networks, I guess. But the way that you typically do that is you do this big compute thing, machines go vroom, and then for each person, you know what thing you might be able to recommend. You store that in the database because it's a very expensive thing to calculate. And then what you can do is you can use that as a cache to go ahead and recommend stuff. Person comes to the website, we might be able to recommend something, stuff like that. However, this would never really work. Because the thing with a second-hand car is, the moment that one person buys it, it's gone, and you cannot recommend it anymore. If you think about Netflix, I can definitely recommend the same show to someone else, but the used car, once it's gone, it's really gone, and I cannot recommend it anymore. And I might have to update the cache, and oops, that is actually gonna break. The update is not gonna be as fast as it needs to be. So you can imagine that with this way of thinking, the team kind of got stuck. We know how to do recommenders, we've got books about that, but this was just never really gonna work. So this is kind of the opposite of a cold start. This is kind of a hot end, basically, which I also thought was just kind of interesting. So then we started rethinking, okay, that's obviously not gonna work. What else might? Well, we started just looking at some cars just sell themselves. It's a phenomenon that we just noticed. There's a couple of cars that even if you don't promote them or anything, you just kind of know that it's a popular car, and it'll just get sold at some point anyway. But we also noticed there were just some cars that were kind of on the edge, like they didn't always automatically sell themselves, even though there probably is a market for it, it's just that people might not have found it. So then we figured, well, instead of doing the recommender thing, how about we do a classifier thing, where we're gonna make a little robot that predicts whether or not it'll sell itself. And if the car that comes in won't necessarily sell itself, we'll just boost it in the search results. So we had this Elasticsearch set up that was actually pretty good at like inserting and removing. It was pretty robust against that. And it had this feature where you were able to boost. So you were able to say, well, this item, put that higher up in the queue. And you can imagine if it's a car that won't sell itself automatically, but it gets a little bit more eyeballs, it actually has a larger chance of getting sold, which means that in total, more cars actually do end up getting sold. So the person might find it. And conversely, and this is, I think, the most interesting thing, we are no longer recommending a car to a person, we are recommending a person to a car, which is like the other way around of thinking about it. And that way of thinking was actually the reason that this system worked pretty dang well. But then you do kind of wonder, what makes it harder for us to consider the thing on the left as opposed to the thing on the right? Because the moment you think, oh, I got to recommend stuff, you immediately start thinking like, oh, the item has to go to the user, and it's a little bit less natural, it seems, to think about the user has to go to the item. And then when you start thinking about why this might be, well, just around the time that these recommenders started getting like really popular, we had this thing called the Netflix prize. This was like, I think, like the $1 million prize people could win. There was some Netflix data. It was like in the time that they still had DVDs. And this was like the one example in all the recommender textbooks. There was someone who won this leaderboard prize, so that's the algorithm we just started teaching everyone. So when you think recommender, you typically think of the thing that was taught, which is this Netflix prize thing, and you kind of maybe forget there's other ways to solve the problem as well, simply because that thing got so popular. And it's not just the Netflix prize that we're dealing with here. If you think about the larger picture, we've also got this thing called Kaggle. There's these data science competitions. It's a very popular website. And that also drives a lot of popularity for approaches and ideas. But you do want to rethink once in a while. And I sometimes wonder, it might not be a hypothesis in my mind, but there are these things that are making it hard for me to sometimes be creative. And some of that has to do with bad advice that people have given me in the past. So when I was sort of a younger data science person, like 10 years ago or so, people would tell me, Vincent, don't reinvent the wheel. Like, we already have some approaches, just go ahead and reuse those. But if you think about the wheel for just a second, I mean, the wheel totally got reinvented like a bunch of times, and that was a good thing. Like, if I don't want to have a wooden horse cart wheel on the airplane, I think that would be a legitimately bad idea. But then, I mean, for us, right, wheels are nice physical objects. We have physics. There's reasons why there are constraints. But if you're dealing with software, there shouldn't really be a reason why you would constrain yourself to one way of thinking about the problem. But it is something that, at least it seems, to be happening. So then, what might happen if we just allow ourselves to rethink the wheel once in a while? I think that's a very interesting and thought-provoking thing to just do more of. And with that in mind, I'm going to work towards a demo now. I'm going to do that by talking about another data set. So this data set is not about the BMI thing. This data set is all about credit cards. And in particular, it's about fraud. You might have seen this data set before. It's a pretty popular data set online. Effectively, it's basically a big table with lots of features of a transaction. And some of these transactions are fraudulent, so we have like a 1 or a 0 indicating was it fraudulent or not. So, okay, how do you tackle this? Well, typically what you would do is you would just attach a model, maybe a neural network of sorts, and you would do something clever because this data set, of course, has a class imbalance. Like for every 10,000 non-fraudulent examples, you've got like 18 maybe fraudulent examples. So there's a risk that this model is totally going to overfit. And you want to be careful with that because it might affect performance, so you want to be careful. And then you read the book, and the typical advice is, well, you do the class weight thing. You're going to tell the algorithm, well, the fraud cases, if you get those right, that's worth way more gradient points than the non-fraud cases. And this is like a general technique that people like to use to sort of combat this class imbalance thing here. But it does feel like we're reusing the same thinking, if I'm honest. Like we're still in algorithm land when we are thinking about this problem this way. And you can kind of wonder, is this kind of a wheel that deserves to be reinvented? Is this performance number really the thing? Is that all we need? Or is there maybe something missing? So I started playing around with this, and I would like to give you a small demo. We have the screen. This works. Cool. So in the background, or in the foreground, I think, let's make this just a little bit bigger. There we go. This is a Jupyter notebook. I'm sure you're all familiar with this. And what I'm doing here is I'm loading in the credit card data set. I'm using polars. It's a super cool library. Go check it out. But the main important thing for the argument here is that it's just a table. I have like feature 1, feature 2, all the way up until feature 27 or 28. And these are all like numeric features. And then there's this class that I'm trying to predict. And most of these are zeros. There's a couple of ones. But I want to come up with some sort of algorithm that can just tell me, hey, was it fraud or not? And just to emphasize, like you can group by the class and do a count. And you can verify that, yeah, this is like imbalanced. That's definitely a part of the issue here. But I still have no idea what's happening in this data set. It's just a bunch of numbers. So my first instinct would be, visualize this. And visualization is actually pretty darn cool, because like an algorithm might scale, and a visualization might not. But a visualization can surprise you, and an algorithm typically cannot. But then the challenge is, how on earth do I visualize like 28 features? That feels kind of hard. Like usually we like to see things in 2D. But in the like 80s and 90s, a couple of really cool techniques got developed to like do high-dimensional visualization. There's this thing called parallel coordinates. And we also have browsers nowadays that are quick enough to render them in semi-real time. So there's this really cool tool from Facebook made this actually. It's called HighPlot. And I'll take a quick moment to explain what you're actually looking at here. But this is what people like to call a parallel coordinates chart. Every one data point in the data set is effectively a line. So this is like feature 1 over here, then we've got feature 2, and the first line had a specific value for like feature 1 and feature 2, and because we've now got every column vertically, the line that goes through everything is basically the one example for my data set. And this package is pretty like neat. You can like switch these things around. You can sort of move them back and forth. You can determine the color, right? So I can say use this column for coloring, and then this will update. But what you can also do is just use the class label to define the color. And in this case, like if it's blue, it's not fraud, and if it's orange, it is fraud. So like the orange, you see that there's a couple of like orange examples that have a couple of values here that do seem a bit distinctive from the blue ones. But that's exactly what we want if you're building a classifier. Like, okay, maybe we don't need the algorithm. So what's kind of cool about HighPlot as well is I can make these selections. So I could like say, oh, I want to select a subset of data here, and maybe only want to select the rows that overlap there. So I'm able to sort of play around with this a bit. And if I can deselect as well. But that also means that if I just grab a pen and paper and I just make this selection here, I can just not forget the values that I've selected. And when I look at this, this seems pretty orange. So okay, let's just assume that everything that falls into this region is just fraud. I can then tell this tool, by the way, to just exclude these rows. And I can see there's actually still a bit of orange left, so I can select that. As I do this, by the way, notice how most things are orange. It's just that there's a couple of blue lines here. Those would be excellent candidates to double check, I think. But okay, let's do like another selection over here. I think with a double selection, I can get a more precise prediction or something. So okay, I'll exclude those. But all right, like there's still some orange in here. But just by using a visualization technique, I can just write down the values that I used. Write a little Python function with an if-else statement. If between these values, fraud. If between these values, fraud. It's kind of like a case-when algorithm. And, kind of, where are my slides? Hang on. Open recent. Oh, there we go. So assume I do all that, and I write those values down, and I do a bit of a grid search. Then I can actually write down the values that I get. So it turns out they're actually not bad. So if you want to perform kind of okay on the credit card data set, and I'm being a bit hand-wavy here because doing this manual work with GridSearch is not the most fair comparison, but still, roughly, it seems like I get like a 70% precision and recall by using a visualization technique. Which, given the class imbalance, isn't bad, but it gets even better, because what you can do is you can go to the Keras blog, which is a very popular deep learning framework, and they have a tutorial on how to use neural networks for imbalanced classification tasks, where they use the same data set. And I really want to, Keras is a really cool project, and this is an amazing blog. The blog post is there to explain how to use Keras. It's not really meant to show the most performant model. But the tutorial ends, and it mentions the precision recall values. And yeah, I guess you could say the recall is maybe a little bit better, but the F1 score and the precision are just way worse than the visualization trick. And I think that's kind of interesting because people do read the Keras blog as an authoritative source. Even though, it really is a great blog. You can learn how to use Keras. You might not learn how to think about models there, but people will copy it. And even more interesting, you should probably not use Keras because you can also use a random forest and get an even better score, by the way. That's also something you can totally do. But now imagine that we just ask ourselves the question okay, is the random forest a good idea here, given the stuff we've just seen in the visualization? And if you think about it twice, then also the random forest might not be the best choice. And let me try to explain that. So before I showed you that you can take the credit card data set, you can explore it. You can build a rule-based system based on the stuff that you're learning. So you can get inspired by the visualization, but you can probably also come up with some of your own rules. But you can take a step back, not worry about the algorithm, but you can come up with a rule-based approach. Besides that, you can have a black box, Keras, random forest, what have you, with something that really tries to fit the data super well without thinking about it. And what you can then do is you can compare the two approaches and see where the gaps in your knowledge are. If the rule-based system captures something that the black box doesn't, why? And if the rule-based system captures something that the black box doesn't, again, you can ask why and actually learn something. This is human learning. But as you do this exercise, you're probably also going to just recognize that you might be able to come up with rules for things that just don't appear in the data, but should be checked as well. If you're a 16-year-old and you have $1 billion on your bank account, I would check that even if there's no example of that in my data set beforehand. That is something like a rule you can definitely add yourself without doing anything with data. And then, if you start thinking about it some more, you might also realize something fundamental about this problem. And that's the issue with the labels, something we saw in a visual. If the line was orange, or if the fraud label says it was definitely fraud, then that's actually pretty easy to trust. Someone probably looked at that, probably a specialist, some human, and yeah, probably the villain got caught and is in prison now, but it's very easy to trust that label. It's much harder to trust the label that says not fraud. Because how can I be sure it wasn't fraud? There's so many non-fraud cases, I can't expect all the labelers have seen all of those examples. And that is something that's, that thought is a lot easier to get into your brain if you don't follow the black box approach blindly. It's a lot easier to get this idea or this concern into your mind if you try to take the breadth first approach, as opposed to, I will apply what I've learned from the book. And I think this is, again, pretty interesting. I might argue that in this case, even if you would have gone with the random forest as the best model, which is something the metrics confirm, it might have distracted you from this very important aspect of the problem. And in my experience, people who have been in fraud for a year or two, they get this. But people who just start working in fraud tend to forget this because they're not exposed to this part of the problem, sometimes because they just overfit on the approach that they're trying to use. And there's a really interesting anecdote, if we think about reinventing wheels, related to the transition from the bike to the left to the bike on the right. There's an interesting Wikipedia page about this, actually. It was pretty interesting. Because there was a point in time where people thought that this is the way you should build bikes. And eventually, people recognized that that might be a much better idea. And the reason had nothing to do with the wheel. It had everything to do with the pedal. Because this was super unsafe to ride. In order to ride that thing, you had to like hunch over, and you would be super high up from the ground. And once the wheel got momentum, it would like keep on spinning. So if you hit something, you would like fly off head first. So people knew something had to be changed, and they had like a direction where the thing had to go into. And eventually we got there. But if you look at the first designs that they made, transitioning from that bike to the one that we eventually wanted to have, you could just see that they couldn't let the idea of the big wheel go, right? And they had a hint. They knew it was super unsafe, but like it took them a couple of years extra simply because they thought that this is how you build bikes. With that in mind, let's now talk about word embeddings. So I'm about to give like the quickest introduction to what a word embedding is, like from a training perspective. I acknowledge that maybe not everyone is sort of familiar with this, so I'm going to be a little bit hand-wavy for that. If you want more details, come find me after. If you want to train like a representation for a word, a trick that you might be able to apply is that you say, well, maybe words that are close together in a sentence are similar in some way or form. And you can argue things like, okay, I can pet a dog, I can pet a cat. Okay, pet and dog is a similarity, pet and cat is a similarity. Maybe if we have a representation for both words, they should be similar. Now, how do you get there? Lots of different ways, but what people typically like to do is like a representation of a word, like an array with lots of zeros, and the one goes into a neural network, and then we try to predict the other words that should be around there. I'm really skipping over lots of details, but it's like a way you could go about that. And if you have a neural network, you also have a hidden representation, and then if you then flip the arrows around a bit, after training such a system, you have a mapping from a word to a vector, and let's call that word embeddings. Lots of different ways you could do this, but let's for now assume roughly this is the general approach. That means, in practice, that if you have a sentence like, have you seen Star Wars, that you would have an embedding for each word, right? Let's call it word to vec, but for each word we've got this vector. And I think this example is particularly interesting because if you look at this example, you can kind of see that there's something wrong with it. Because if what is similar to star, right? We have a representation for the word star and a representation for the word wars. But if I take the average of those two word embeddings, am I then close to like Han Solo and Chewbacca and Darth Vader? Maybe not. I mean, it's more likely that if you have the word embedding for star, that's maybe close to universe, and wars, maybe you're close to like battle or something like that. But the whole concept of Star Wars is like its own unique thing. It's not, you cannot just merge two words and hope to get the same meaning out. But that's a hint. And we might be able to leverage that if we think about tools that we have available now, which we didn't have 10 years ago. I work for a company called Explosion. We have this tool called Spacey, and Spacey can provide you relatively reliably things like part of speech. So we can estimate whether or not a word is a verb, and we can estimate whether or not it's a noun. And to make things even better, we even have stuff for grammatical dependencies. This is a statistical model, it's not necessarily perfect, but if we now rethink what we're doing, you can notice that we have like a compound noun there. And we also see that there's this grammatical relationship from the verb that goes in, and you can kind of wonder, maybe on top of that graph, I can just come up with some heuristics, such that I say, let's chunk the nouns together, and for all intents and purposes, pretend that that's a single token. So instead of seeing star and wars as like two separate words, if I apply like some grammatical models and if I can sort of figure out a heuristic to chunk them together, maybe, just maybe, I can repeat the same word to vec thing, but I just change the meaning of a token. A token isn't a single word anymore. It's much closer to something like a phrase. And if I think about stuff that you typically want to detect, like when you're doing named entity recognition, you're typically interested in like noun chunks, not separate words. You're interested in finding a concept. But that means that maybe now, Star Wars as a noun, like because we still have the part of speech stuff, what happens if that's now a token? And that's pretty interesting because it also means that duck as a noun might also be a different token as duck as a verb. And I can have different word embeddings for both. And we might end up with phrase embeddings. This is a really neat idea. And again, my employer has this package called sense2vec that has these embeddings. It was trained on Reddit. And you can really rethink what similarity means now. Because we're not talking about words anymore. We're definitely closer to phrases and perhaps even concepts. Still, like, the algorithm will never be perfect, but just think of like a demo of what you could do with this, right? You can go to the online demo, and you can type in Knights of the Old Republic, which is a video game that I used to play back when I was like 18. It's a Star Wars-based video game, like it's super nerdy. But if you then ask the system, like, hey, what are similar words based on like the embedding of this phrase now, and we use something like cosine similarity, like what are the other similar phrases, then you get Knights of the Old Republic with capital letters. You get KOTOR, which is like the online abbreviation for the video game. We get abbreviations for free. You know, that's actually like a huge problem usually, but those are in there. We get Jade Empire, similar video games. We get the Jedi Knight series, Mass Effect, different spellings for the KOTOR abbreviation. This is a really useful embedding, especially when you start thinking about how you can use it. So let's say I'm interested in like finding video games in text. I mean, I can start with something I like to call a seed phrase where, okay, I'm interested in finding video games like Knights of the Old Republic. Let's use it as a seed. Let's get the embedding for that. Then I have my unlabeled data with lots of phrases, and what I can then do is just say, well, go over the phrases one by one and just find me the ones that are similar to the one that I start with. Again, cosine similarity is what I'm using. Most similar to go first. And then me, as a human, I can just curate and look at the most likely candidates first and not have to go through an entire data set. There's like a cool little human in the loop. And what's more, maybe at some point I've exhausted this seed phrase, but that's okay, because I can reuse the other entities for this. And I can actually look for concepts in my text. And because this thing is trained on Reddit, you know, we also have slang and abbreviations. So even if you don't have perfect spelling, we're, I mean, not perfectly robust, but there's some robustness against this. And how on earth would you have gotten here if like your first notion of, oh, I'm gonna do entities is just basic tokenization, embedding, feed forwarding that to a neural network, and then hoping that we get the right thing out? Like, the hard part is usually finding the great labels. So maybe we gotta focus on algorithms that can help you with that. And then once we have good labels, we can maybe do the basic thing. But this is, again, like one of those ideas that feels hard to grasp if you're so trained to think about this problem in a certain way. And maybe we're distracted from great ideas just because of the way that we're used to thinking about it. And that got me wondering, like, what can I do to ensure that I keep on getting great ideas in front of me once in a while? And I'm partially doing this because Twitter isn't what it used to be. So let me explain my new hobby. I really like to read archive articles that introduce a new data set. And the reason is because when you introduce a new data set, you typically also have like a really weird and novel task, and I just get a lot of inspiration from it. And just to give an example of stuff that I've seen, there's this data set that mentions a comprehensive gold standard and benchmark for comic book text detection and recognition. So, you know how comic books have these speech bubbles? Turns out that's a really interesting NLP and OCR problem, because they come in all shapes and sizes, especially when you get to like comic books from the 50s, which is what they do. And not only did they collect the data set, they also like have introduced a new model, etc. But this is great. Like, I'm rethinking my approach here. This is not something I do every day. This is inspiring. And you know, I have a tool for this now. Like, there's tons of people doing agriculture photography now. So if you want to have greenhouse tomato photos, I mean, there are tons of public data sets about that, which is cool. I'm not into Dungeons and Dragons, but apparently there's this professor that collected like role-playing game transcripts, and they have like a giant corpus for like learning character action interactions, which is something LLM people like to do now. But there's also other topics, right? Like, data sets are super cool, but there's actually like some good psychological research on how people like to code, like developer research stuff. And like, is Copilot good, and can we measure that? I'm also really interested in data sets that talk about model error, like label errors. Turns out that Cypher10 has duplicates between its train and test set with different labels. And like more and more people are investigating these public data sets for errors. And that's also like a huge favorite topic of mine. And I would love to have a system that brings me stuff that inspires me. I would like to consider that a hands-on problem nowadays. Again, because Twitter's not what it used to be. Lucky for me, archive is public. The giant API for all these PDFs is something that's publicly available, so I can scrape that. So that means I just need to build a classifier. Except, this is actually one of the more interesting classification problems I've ever seen. Let me explain that. So you've probably seen these pictures on the internet where they do the embedding thing, and then they do the UMap thing, and you get this pretty two-dimensional visualization thing that gives you the impression that there are all these different clusters. And what you kind of hope for is that these clusters are kind of well-defined in hindsight. So maybe there's like a little economics cluster there, a little NLP cluster here, and like a biology cluster there. And if you're doing like text classification, that's exactly what you want. But are we really going to have a separate cluster that only has data sets? Or is a data set something that actually appears in every cluster? Because you have a data set in the field of biology, and you have a data set in the field of physics, and you have a data set in the field of NLP and everything. This is kind of one of those topics where the overlap of text is actually super big, and it's a pretty tricky problem if you just think about all the challenges. The input for the system is a pretty big abstract, and because it's big, it has many topics. And I can definitely see how it, just try to read this in a second. It takes a while to read a whole abstract. And if it's hard for you to annotate, it's probably also hard for the model to immediately figure out what to do with it as well. So take a step back, can I rethink this? And then very quickly, I just kind of noticed that a lot of the time, not always, I can also just read one sentence from the abstract, something like, additionally, we introduced Tomatopedia, a new large and challenging data set of greenhouse tomatoes. And then I can just kind of go, yeah, that's enough. If a sentence like that appears, I don't have to read the rest of the abstract, basically. I'm done. And sometimes there's two sentences like that. But maybe I shouldn't think about this as standard text classification. Maybe I can redefine the problem and just make it simpler for myself and just worry about sentences instead. All right, how do you do that? Well, the luck is that this is archive, so it is pretty well spelled out. There's no social media spelling or anything. So again, I can reuse Spacey to split this up into different sentences. And then for each sentence, I can have a classifier. And then, the score comes out. And if the score exceeds a certain threshold, algorithm can go, found one. But the really cool thing about this observation is that you shouldn't stop rethinking here. Because if you take a moment, you will also, again, remind yourself that just like it's hard to model an abstract, and just like how modeling a sentence is relatively easy, if I have a sentence model, the same might hold for annotation as well. I don't have to rethink just the model, I can also rethink the way that I get my training data, because I really am starting from scratch. So, all right, sentence model, cool idea. I have this approach where I'm collecting abstracts, and I might classify that later. But that means that now I can start dreaming a little bit about how I'm going to do these annotations. And that might lead to a pretty fun demo, too. So, by the way, this is my front page. This is the artifact that the system generates. It is an HTML file. I can click the name of a data set, the name of an article, and the system will tell me which sentence is a sentence that made it believe it was about a new data set. It gives me a little confidence score as well. And there's a config file, but okay, I can click the link if I want. But let's open up another one. Maybe this one is pretty interesting. Oh, hang on. This one has the sentence, experiments show that our method achieves state-of-the-art cross-dataset reconstruction on 5 zero-shot testing datasets. This is a wrong classification. And what I could do is I could say, well, let's hope that active learning will fix this. But I can also say, well, in my live system, I see something that my model does wrong, So what I really want to do now is find examples like this and annotate those first. Because this is a thing my model does wrong right now. I don't have to worry about probability values just yet. I could just annotate this. So what I also did is I kind of made this really cute little interface for myself. So I can say front page, Python-m front page annotate. And this is going to boot up a bunch of custom stuff for me. I can say I want to annotate a new label for a new data set. I want to annotate on a sentence level. I want to annotate using an approximate nearest neighbor trick. And I want to find examples similar to this one data set, this one example. You know, it takes a while to boot up, but eventually it does burr. And then I get a labeling interface where I can kind of zoom in. This is, again, a sentence that's not really about a data set. It's more about a benchmark on a data set. So this is something I'm indeed interested in labeling. I can hit no. This also feels like it's about a benchmark. So again, I can kind of hit no. And I do this for like 15 minutes. I have about 50 or so examples maybe, and I can retrain. And this is kind of nice because I can literally steer my model into like fixing the bugs that I see it do. And what's actually kind of cool as well, like I have sentences, right? But I also have abstracts, so I can leverage that. And I can do this trick that I like to call second opinion. Because if you have a model that's actually kind of okay, you can also spin up an interface where it actually just loads up the entire text, and it just tries to like highlight the sentence that it believes is the reason why this should be about a new data set. And, I can have a look at what it gets wrong. I can kind of say, well, add this sentence, kind of do the UI thing. But if I now accept this entire abstract, my sentence model will get 2 positive labels and about 8 negative labels. And suddenly, by annotating 1 abstract, I get about 10 examples to train on. And that's actually kind of neat, too. Like, if I spend more effort per example, my algorithm also gets more examples from it. And there's more than one way to annotate this data set. And the odds of me getting surprised, similar to the visualization trick, is pretty high, too. And again, the only way you would kind of get here is to sort of let go the idea of how you should do active learning. You can kind of determine that yourself. And I started, like, can I name this? Like, normally, if you read a book, like, how do I annotate? You kind of read, well, you take your trained model, and that model determines what to prioritize. But maybe this idea of active teaching is also just kind of cool, where the whole point is that I, as the person who understands the problem, is in charge of telling the algorithm what it should learn. And I can come up with all sorts of cool tricks to help me find data sets that are relevant, like stuff that gets wrong, or just a couple of heuristics that make it likely for me to get examples that I'm mostly interested in. And there's definitely more than one way to do this. And I find it very liberating to sort of rethink these things, simply because I'm afraid of getting stuck. And looking at the time, I won't go over all the details. There's a bunch of rethinking that you can also do when training this system. Because technically what I'm doing here is like multi-label classification, but there's a couple of missing values as well. Like if I'm annotating for multiple labels, it's pretty likely that I won't ever have a text where I have a label for every example. So I cannot just pass it a matrix with lots of non-values. Scikit-learn doesn't really like that. So for that, there's this other trick that I do, where basically I train a system and I do the for loop, train one label first, then the next one, then the next one. Respect for time. But I think it's fine to skip those details because we're kind of getting to the point of the talk, I guess. Hopefully I've been able to show you some neat ideas. And you might get inspiration from this, and you might think, oh, I can reuse these ideas. And you should, but it's not the point. The point isn't that from now on we should recommend users to items all the time. It's also not the point that you should always get inspiration for visualization first. And even though the sentence model and all the active teaching stuff I've just shown you I think is really neat, these are just examples. The point of this talk is a little bit more on what makes these ideas possible in the first place. Or rather, what sort of things around us might block these ideas from happening. Is there anything that prevents us from rethinking wheels when we need to. And that brings me to a bit of a fear of mine in this day and age. Because I think that we might want to worry that the current generation of data professionals actually grows up thinking that we have actually figured out how to think about data problems. And the issue really isn't tools, but really the way that we think about them. Because in real life, you have a real-world problem that you translate to a data problem, then you flow your tensors, you do your math stuff, and maybe you get a model that's in a better state with a number. This is data science, right? But it's not necessarily guaranteed that the translation back to the real world works. Like, the algorithm might not survive the impact with reality. And yet, if I think about where most creativity goes, if I talk to data people, they tend to love to talk about the left side of this diagram. There's not too many conversations about like, hey, are we solving the right problem? Are we thinking about this the right way? And if I have to take a step back, I think the issue is that we might be used to a certain way of thinking and that there might be this little monoculture around that. And I like to call this the optimality trap. Because it can be so tempting to chase a single number and like completely drive into that rabbit hole, especially if you surround yourself with peers who have the same training. And I don't know, like maybe you forget what it can be like to have new ideas. And that's scary to me. And it's not just in models that you have this. I think the whole MLOps thing also suffers from this a little bit. If you're knee-deep in a specific like stack and all the tools that belong to that stack convince you that this is the way you should do machine learning, how on earth will you ever consider an alternative? Or maybe even worse, maybe you're so invested in your way of thinking that you actually believe you're optimal while being completely blind to the gorilla in your data set. You'll have the most state-of-the-art tools and totally miss out on the problem part that matters most. So the most interesting thought then is maybe how can we actually find this gorilla, metaphorically? So I do think, in general, tools and knowledge are good things. If, for example, you didn't have the skill set of a programming language to make this chart in the first place, it would not have worked. Like, you do need tools and techniques at your disposal. And also, we've got like decades of computer science that we can go ahead and reuse. We can apply first principles. So in my mind, it's probably not the tools that are the issue. Maybe the way we think about our tools is the issue. And that kind of brings me to that article in the beginning. Like, if a hypothesis can be a liability in statistics, then in our field, maybe familiarity is also a liability. If you're really trained to think in a certain way about your problems, by being familiar, you might trigger this, oh, I know how to do this reaction without even thinking about it. And that's not always a bad thing, but it can be a liability, and sometimes it also can be a tragedy. And that's mainly if you're eager to be seen as an expert. And I feel I should mention this both as a recovering consultant, but also in this era of data influencers. Expertise can also be a liability if you think about it. And here's what I mean by that. Like, if you want to be seen as an authority, you really have to convince yourself that you know what you're doing. Like, you have to double down on it. And that promotes tunnel vision. And if you convince yourself that you figured it out, it becomes a lot harder to recognize that you might need a new idea. It's a lot harder to be creative, and you might get stuck repeating the same trick. And if this is the reason that we're missing the gorilla, that will be an honest tragedy. But there is a bit of hope if we think back about this again. So in this case, that feeling of this is how you design bikes is precisely the thing that made it harder to design a better one. But we did get there. And the reason was, we had a really good reason to doubt. We knew that something was wrong with that pedal. We knew it was unsafe, and that at some point people just caught attention of it. They were doubting the original design, and because they had a good reason to doubt it, they were able to take a step back. And during this talk, I've given a few examples where an improvement was made, and if you pay attention, you may notice that each of them was kind of sparked by doubt. Doubt can be an escape hatch. There was a notion that the original plan had flaws, and because we were able to pay attention to it, we were able to sort of escape. And it might be a generational thing. Like when I started ML, there were just not enough tools for everything, so we just knew that we didn't know everything, so we just tried a whole bunch of stuff. And I'm a little bit worried that this generation is forgetting to do that. So just some advice, like grant yourself a blank canvas once in a while. Like really give yourself the space to think less about tools and honestly think more about ideas. Like make time to reflect, try to understand the reason of doubt as much as you can. And also like grant yourself some time to play, because you can be a serious person without taking yourself serious. Because if you do that, you'll be much more receptive to great ideas that will genuinely get you unstuck. And I also have some good news, because if you want to do these things, natural intelligence is all you need. Because I don't think we'll get artificial doubt anytime soon. And the main point is that natural intelligence is something that we all need. I would really prefer a future where you're always able to think for yourself and to come up with your own solutions, instead of being limited to the tools that some vendor gives you. And there's way more than one way to think about a problem, and it'd really be a shame if we ever forgot that and got stuck. So please grant yourself creative freedom, because otherwise you just risk on losing some great ideas. One more thing. That archive front page thing I made, you can fork that. Like that's on GitHub, and I would love it if people sort of take inspiration from this and start doing this too, but for topics that you are interested in. And what I would love even more is that if you find really cool articles, that you just start a little blog with a Today I Learned section, which is what I do, where I have blog posts with like maybe 1 or 2 sentences, basically describing the cool idea in the article, just to make sure that that idea is archived and doesn't get forgotten. Because again, ideas are fragile. I didn't have enough time to talk about everything I wanted to, but if you're interested in this data set and how we model this, I am giving the workshop on labeling later today, so you can actually play around with these labels. So if you're interested in that, do come by. I'm also at the Explosion booth. And I guess the main thing I want to say is like, thanks for listening, and